is not completely teach. Purpose is to show what we are learning, how you can apply. It is applied. So I start with very basic. For example, so far you have learned quite a few things. I will repeat many things, but you will soon see that even if repetition is there, some subtle aspects will come out. So QIQT you have seen 1 0 rotation is 0. This bracket rotation is due to drag. So bracket. For example, this is K. And what is this object called graph? This is the dagger of the K. So 0, for example, is 1 0. If you take so-called dagger means this is called dagger. It means transpose for the matrix, and then on that compress combination. Compress combination. So I will be using different colors and we drag up. So now 1 0 dagger is very simple. So row becomes column, real elements. So 1 0 becomes 1 0. Now you may ask, so then same thing, for example, there is another fellow called 1, and that is your 0. And these are all standard vectors in 2 dimension. Here the 2 dimensional vectors. For your convenience, you can imagine them as the plane x and y. And there are typical vectors. A, for example, like components ax and ay. So you can think that way also. For example, a typical vector A can be written as I times ax plus j times ay. If I write this way, it gives me a simpler feeling, I don't get scared. So it is also good to compare what is the difference between this normal classical vector which we have seen, dealt with, and these are quantum objects. If you treat them as quantum, purpose of this is to bring out that. So in 2 dimensions, how many unit vectors you need? 2 of them. Unit vectors. And dimension is 2 units. In this case, what are they? I and k. So unit vector I is along x, vector y. So keep this in mind. Orthogonal complete set. This is a concept we always come back to. Orthogonal complete set. Orthogonal complete set. And I am going very slowly. May look boring, but keep in mind that this is actually very important because when you go to abstract domain, always have to keep in mind orthogonal complete set. What is orthogonal? Remember, I square is equal to 1. First of all, normalize j, and then height of j is equal to 0. So you may imagine why did it come? It actually came, if you look at it historically, for time keeping. You know, they will have this Swan diagram. They will stick Swan-like balls, and then it has projections. So all these words like projection, project geometry, they came through that. How sunlight enters the house. So very nice. Orthogonal complete set. If I have one vector I, it will not be complete. If I go to 3 dimensions, we are all familiar. I, j, k. I and j will be orthogonal, but not complete. So orthogonal complete set. And why do we normalize to 1? Because it's like a kilogram. You know, if unit is 1, then only you can find out the component. For example, how do I find out x? I have to project x direction and I find a. See, if it is unit vector I square equal 1, I dot j equal 0, I get only this object. So it's like a kilogram. In the unit of 1 and the component is x. So you can compare two different vectors if this kind of unit vectors are introduced. So mathematics always comes from requirement. So very good. So these things all I know. What is new in the quantum domain? So far nothing new. 2 unit vectors, matrices also found vectors. And as you know, we came to matrices by solving linear equations. If you have 2 linear equations, we found we can cast them in the language of matrices and use the matrix inverse, solution becomes easier. So mathematics developed as requirement also developed. So very good. So now, just like A, here is an arbitrary state. Here, what is an arbitrary state? You put it this much. and we call it alpha 0 plus beta 1. Compare it with here, same thing ij, unit vector 0 and 1. So 0 square, it's not 0 square, 0 matrix, 1. Same logic that we gave here. If we don't normalize it, then how do we find the component? For example, if I want to find out the amplitude, just like it is there, I take this object 0 and project psi along this direction. You get that find alpha. So alpha is like to AX. So mathematics is identical, and we call it, exactly project this one, and the rotation is this. So now here we have Cartesian coordinate. Now we know other coordinate system, for example, cylindrical coordinate system. We know r and theta. So similarly here, there is nothing unique with respect to this basis. Then have so-called Hadamard basis. Very useful. As you what we see, so-called Hadamard basis, which is plus and minus only. Some of you might have seen them so far. So this object is 1 by 0 plus 1. And if I do plus minus, minus will come here, plus will come here. Now if we expand it, what is this object? This is 1 by 2. And 1 plus minus 1. And you can check 1 by 2 is for normalized. Is that the only one? Answer is no. Generally, there is another one which is used. And emphasizing this because these bases are very important for quantum field distribution. So that's something I'm defining. There is another one which you might already see. They are actually something like 1 by 2, 1 plus minus I, which is also normalized. So note I is there. If you compare with light, this object is circularly polarized light. Left circular, right circular. This is actually 45 degree. You know that 1 plus minus 1 is 45 degree. Okay. So that you can check. Circularly, it always helps to think in terms of light. Circularly polarized light, left and right. 45 degree. 0, 1 is horizontal vertical. So this notation you must have seen if you read QIQT. People also use this kind of thing. For example, 0 horizontal vertical. Now you can go back. Horizontal vertical. Okay, so that is G1. And then if you see, for example, QIQT, this protocol, sometimes people will denote something like this, a state like this, and another state like this, if I remember correctly. We are actually 45 degrees, these objects. Then comes circularly polarized, some circle kind of thing. So, the Bennett and Prasanta will give that engineers, very pragmatic, practical people. So they use this horizontal vertical, X and Y. The light is going along some direction, the two polarizations are there, that's what they use. And they give this arrow, 45 degree like this. Because I know Prasanta, was in Mr. Control when I was a postdoc, very practical man. He will always use this kind of geometric language and play around with the two world matrices. Very good. So left circularly polarized light, 45 degree polarization, and which is your Hadamard state. Then this object 0 and 1 horizontal vertical. This notation is precisely what they use. So instead of these times, our TIC people or math people use plus minus. Because Hadamard did it because we got it from what? So these things you must have seen, and they are the things which comes from this two-dimensional space. There is nothing new. They are very much analog of different bases like I, J, R, theta, cylindrical basis, those kind of things. So far, no, nothing quantum. Everything is like vector space. So now you look very carefully where quantum comes. Very good. So first of all, I have to normalize. So now let me see the difference part I get. The classical domain and quantum. Now first I have to normalize. So psi was 1. That implies we can compute. For example, this object psi is actually, if we expand it, this is alpha beta. In general, they are complex numbers. this object psi, the dagger of this fellow. Compute the dagger. That's it. Transpose and star. That's what it is. Now what? Explicitly to do it, what you find? You find the number alpha star alpha, star beta, alpha mod square, beta mod square, so very normalization. Physical what does normalization mean? It means they will represent, for example, an electron. That all over the world, if you sort, you should find it. That is exists somewhere, probability equal 1. So that is the meaning of normalization 1. If you do continuous variable states, typical what we do in case of quantum mechanics, we integrate it. That means the wave function normalized means everywhere you sort in the world, it makes particularly there somewhere. So that is the meaning of normalization. And this mathematics we got new, so nothing new there. So and this is called unknown state or arbitrary state. Typically used, for example, part of teleportation, they teleport an unknown state. Why unknown? I do not. So unknown state or arbitrary state. And they say now there is some ambiguity when you deal with waves. What is ambiguity? Ambiguity is, people might have already told you that if you take a wave function, you ask writing minus of the wave. Do they give the same physics or is it really different? The minus sign taking it. Answer is they give the same physics. Not only that, if you multiply by phase also, physics does not change. That people knew again. Why is it true? Because whatever they measure in quantum mechanics, there are objects like this, or some operator, expectation value, the matrix element of operators. You can easily check if there is a phase. In this case, this phase will not exist here, and this one would have an additional phase minus I. And it will pass through theta is a number, you cancel. Same thing here also. So overall phase therapy. Because of this reason, people like online from very early on, they pointed out that instead of dealing with the wave function, it is better to deal with something called density matrix. This type of one we introduced, why it was required, and it is this object size. What is this object? Let's work it out. So just for the sake of completeness, so this is the so-called, I think if I remember correctly, it's called outer product. I don't know the name. How do you multiply? For example, here, this object is alpha beta. I know that. This object is whatever that thing is, alpha star, beta star. I'm a physics person, mathematics will tell you why are you writing like this. But what I really mean is how to do my calculation. So I will actually take what it means is this. Alpha times this fellow, beta times this fellow. So this becomes a matrix, 2 by 2 matrix. The outer part. So what is it? This is alpha star alpha, alpha beta star, beta alpha star, and beta star. So 2 by 2 matrix. So outer product. I started with a column vector. 2 by 2 matrix. This is a number. So this is the dot product or scalar product, the number. So this is what it is. So mechanically you will see this ambiguity is not there because it's going to slide it here. So phase ambiguity is not there. That's the thing people like one another when it happens. So they said they will deal with this kind of thing. For example, for the so that you can compute easily. So very interesting property you find, for example, let us compute, let us take psi as 1 is 0 and the other two are 1, they are closed. So psi is made out of 1. So what you observe? Let us see 0, 0 if I do, what do I find? 0, if I do, I find that 1. can check that. This object is 1, 0. Outer product, whatever you call it. 0, 1. So we see 1 times 0, 1. Am I making a mistake? I will use. Right. Then it is 1. And 1, 1 is how much? 0, 0, 0. Okay. So what you observe is that if you are both of them are present, you can check yourself that trace of row was equal to 1. Because this reflects on else. Take here, trace of row is 1. 1 is only. And if you have only one term, either this is present or that is present. If there is only one term, you can write the matrix of that only one term or one diagonal term. They are called pure states. Just language, only one term. You see more of these things later. These are called pure states. I tell you a little bit more, but if there is only one term, this object has only one term. Okay, in whichever way you diagonalize, finally, if there is only one term in present, they are all. That means this rank of the matrix is 1. Only one term is 1, 0. Then it is pure state. For pure state, trace of row is equal to 1 because of this value. And row square is equal to row. And check that row square is equal to. Want me to check or you can check? Row square is 1, 0, 0. And now multiply matrices. 1, 0, 1, 0, 1. 0. This is a projection operator. Row is equal to 1, row square is equal to pure state. Why is it useful? Keep that in mind. Trace row is equal to 1 is not so row square is equal to row is very interesting. Suppose somebody gives you some row, you don't know what it is. Ask you, is it pure or is it mixed? Then asking you to do this, row square is equal to row is pure. So purity of the state people say, so this keep that in mind. So very good. So give me an example of, for example, mixed state. Mixed state is more than one. Right? Satisfying all the properties. You can easily check. Mixed state will be add them up. Row or a mixed state. One simple example. Half 0, 0 plus 1, 1. There are two terms present. So add them up, what you find? Half ID. Okay. Again, you see. Trace row is equal to 1. Normalization means half here. But row square is not true. There are two eigenvalues only. This is an example of mixed state. So, and it is of course diagonal. This is a general term. Now, you may ask what physical state it represents. So, many of you must have seen light. You know that in case of light, you have this Poincaré sphere, right? So, polarization of light. Please read the chapter of bottom. Very beautifully written. In polarization, pure states are on the block sphere, on the surface of the sphere, and inside that, those objects are called by origin. They are called partially polarized light. Partially polarized light. Whatever language you need for quantum mechanics is there like partially polarized light and the points in between. And this origin is completely unpolarized light. Completely. Everything is one. There is no information. Completely unpolarized light, there is no information. Whatever can you get out of it? Nothing. So completely unpolarized light, partially polarized light, and surface fully polarized light. Fully polarized light is pure state. Inside that is mixed state. So if you are hecht or water, beautifully everything is there. They deal with these 2 by 2 matrices and nicely. Then later on, Pauli use them for quantum mechanical spin. But actually, credit goes to optics. they have created these things to describe computational biology. Many of the mathematics developed primarily because of objects. So Kolkata or any book you follow, you find it. And this always helps because I can always imagine mixed state what is it? Partially polarized. Partially polarized means I can still recover some polarization. That what is it called? There is some name for it. There is a distill. I can distill some of the states which can be polarized. This kind of words you will come across. Very nice. So now, in general, I have taken alpha beta and I have shown you that this matrix I have already multiplied alpha mod square, beta mod square, alpha beta mod. These diagonal fellows are called coherence. And this represents of diagonals. These objects are like intensity. This is coherence. You will see more of it as we go along. But you see complex. And trace rho is equal to 1. We get Q. Alpha mod square, or beta mod square, the trace diagonal. That's normalization. And you can check rho square is not rho in general. If rho square is equal to rho, this is pure check. So now we are familiar with this object, and we saw the need to go to this kind of matrix. First of all, to make it ambiguity of faith. Then it gave us something more. It told us how to describe mixed state, namely partial polarized. That you can never describe using waveforms. So therefore, if you see Kahneman's book, you will find statistical mechanics plus quantum mechanics. He gives it at one go, completely one. Both the things are in combined. Feynman's book also you see this approach they take because at one go, ambiguity is not there. You can do statistical mechanics, namely partition function, and also quantum mechanics. So very good. So right has all these things, dividing matrices, nothing very big. So far we are doing the matrix multiplication, vectors, or nothing more. Now let us go to measurement. That actually we bring out the difference between classical and quantum. There are the profound things which we come out of that. So now I have an electron or a light which has a polarization like this. So that object, analog theory alpha 0 plus beta 1, which I can write as alpha beta. Then I asked, what is the meaning of something analogous to projection? That if I want find out along x direction, what is there, what do I do? Classically, I did a projection, I got it. Vector is not disturbed after my measurements. This vector remains intact. Right? You must have seen book speak. There are according to the movement of the sun, there will be shadow along the x direction, along the y direction, along the z direction. For example, those are not going to be disturbed by looking at it. So experiments or measurement does not happen the same. Now you look at quantum mechanics is where the difference comes. This is called open again interpretation, collapse of the wave function, many things are there. And let us see how it really works. Because all these things right now, what we are doing, quantum distribution, many things, algorithms, they all depend on measurement. Therefore, please cut it here. So this state is given. Now you ask, 0 is along x direction. People have some vector, call it x and y, no problem. This direction is that of 0, this direction is that of 1, they are orthogonal, unit vector, 0 and 1, like I and j, x and y. So then I ask, I use this basis for measurement. But still it is similar. Am I going to write it in Cartesian coordinate or in terms of r and theta? So therefore, so far no fun. I fix my measurement basis. But that is the point. Take given measurement basis. What is the measurement basis? 0 1. That is outcome. Outcome. What's the measurement actually? Then measurement outcome. You must have seen books. This is typically given like this. Or some write it like here. Measurement. So outcome of the measurement is that this fellow collapse. So this word collapse of the measurement. For example, if you do one measurement, or only one, only one measurement. What is the outcome? Only one measurement. Outcome would be either 0 or 1. So please note that. One measurement. Measurement is like putting analyzer. Light is going. Now you polarize the light. Namely, you can create 0 or 1 by putting polarizer. Analyzer is another polarizer, you see how much light is coming. That is amounting to measurement. Classically, you know this Malus law. Okay, there will be cosine theta, sin theta kind of thing. That is classical. Here what you see is that after measurement, state will collapse to 0 or 1. And nobody knows which one. Completely applicable. That is what engineers get confused. And what outcome nobody knows. Now, so this actually is the now you do many measurements. What we find? We find many that is one many. If you do many measurements, then what we find is 0 will occur with the probability. What? A number square. 1 will occur with a number square. The question of probability comes. So that is quantum, and after that, you know what will happen. So that is, then you ask this question. This is my fifth point. So one measurement, many measurements, measurement outcome I know. One measurement is 0 or 1, completely identical, which one I have no idea. Thousands and thousands of measurements, probably I'll come out square and get 0 will occur, beta mod square times 1 will occur. If I do infinite number of measurements, not to infinity finite, then there may be some ambiguity. Half the number increases, I'll find that. So this collapse of the wave function is Copenhagen. This for and it could be developed Copenhagen. You can see the picture. And so far, experiment Einstein was not compatible with it, but it has experimentally found it. This many measurement lead to this. This is due to Born and load and Born bodies. Statistical interpretation of quantum mechanics. Like in statistical mechanics, probability was there. This interpretation Born. So what is the state after the measurement? The state has changed. Now it has gone. So this is the fifth point. State is equal to from psi. Now it has gone to either 0 or 1. Because after n number of measurement you do, measurement outcome is only 1. So there will be alpha mod square numbers of 0, beta mod square number of 1. But state finally will be 1, 0 or 1. This is the difference. You see, here you try to see in which A is where. Okay, there is a component X, there is a component Y. You try to find out A remains intact, nothing happens to it. But here there is something very funny that state has changed. For example, you know, this please appreciate. Psi is like a vector equals here. You can say this psi. I'm using like vectors. So post measurement, state will be either this or this. State has changed. So now this I ask everybody, some of them make mistakes. Will it be like 0 or 1? Or will it be like alpha times 0? The question. It should not be alpha times 0. You do not remember at all about alpha. Why is that? It will only 0. Because this fellow has been normalized. Psi mod square into 1. If alpha would be there, then there will be trouble. Because normalization will be alpha 0 times 0 alpha star. That is alpha mod square. It is not 1. But measurement leads to collapse of the wave function. It doesn't kill the wave function. If alpha mod square is there, means beta mod square is gone. That means electron number is decreased. That cannot happen. So answer is that this is not true. State will collapse and answer will be only low. This is very interesting. Then you play around. You say, oh, that is very nice. So if I do now my measurement with plus minus basis. What will happen? Plus minus basis. What will happen? So first of all, the O basis you define, you ask the orthogonal and complete answer. Yes. Then you go on right in terms of that. So if you do a little bit of mathematics, if I remember correctly, this will be cross, please work out. All I will do is that what we like. Cross take it 0 plus 1 and minus take it 0 minus 1. So what do I do? I find 0 in terms of plus minus. 0 is equal to R10. How much is that? To R10, you get 2 times 0 is equal to plus minus, right? Yes or no? So therefore, 0 is equal to plus minus by 2 and by 1 is equal to opposite side plus minus. So let me do that. I will take this object and if I put 0, then we plus and 1 would be this two will add up. So alpha plus beta by here. Both of them are minus beta by. So again, if you measure, what will you find? Plus minus basis measurement. Answer would be this slowly plus or minus. Answer. Complete. This is what box engineers. Whatever basis you measure, final state is that. What is going on? This is the real application of mathematics. But engineers are smarter than physicians. But see, engineers are quite smart. So they realize here, very nice. Alpha plus beta is alpha minus beta is coming here. So I can do something. What can I do? You can use a quantum state and a measurement to add numbers, subtract numbers. So additional numbers, so somebody's different state. If coefficients I want to add, states are given. I created in using polarizer analyzer in this state. I want to add these coefficients. You can actually load number one want to add and take the state, measure it plus minus basis. And you get alpha plus and alpha minus alpha plus beta, alpha minus beta. So measurement. So there was a boy here, Prof from Pune, second year civil engineer, did not know much, interested into quantum computation. When he saw this, he designed a quantum calculator. Let's say in my archive, the quantum calculator developed. Very nice piece of work. They were published it yet. Sent it to some command or something, or even resonance. They said, well, it's too simple. But you can check it out. How we develop plus minus through measurement, then multiplication. How we multiply, I leave it to you. So in fact, so you can do computation using measurement. So this actually, when we are doing, we came across this thing. There's an entire new way of doing computation, which is unique to quantum computer, is measurement based. Now it's numerical. Through measurement, you can do quantum computation. Everything, only through. And step that is used for showing that is called cluster state. It comes very, very useful. And this Austrian group in Vienna, they showed it. Measurement based quantum computation is quite unique. Classically, you cannot have this. That you can do every question, factorization, addition, subtraction, big algorithm, everything that you can only show. So it's very, very unique to quantum. Nothing is there in the classical world is compared to this. Okay, this one very easy to play around. So very nice. So for example, if some of you have played around with an IBM quantum computer, otherwise you ask computer to introduce you. I suggest you go there, you know, create. So what you do, draw one line, IBM, then you know, create take 0, then put an haraman, you can drop, drag and put it here, create cross, then do measurement. In measurement, which basis? 0 1 basis. For yourself, find out tomograph half. 50% is for 0%. This will find and check. Actually, find slightly different. If you find slightly different, you are actually showing that the IBM quantum computer is not a program. There is no problem. What the problem you ask IBM, they tell you that 0 is the ground state. So that is always true. One guy may have some leakage. One fellow can either it can compute the environment or it can compute the higher states. So you will find out there is one aspect. So you are actually seeing a real quantum computer measurement statistics that we find. Just play around. So I have now introduced a gate. You have to do some work, something one by one. And it's Hermitian, matrix, unitary. So these two properties, please remember, Hermitian and unitary. Hermitian matrix and unitary. Hermitian means it's dagger in equation. For example, in quantum mechanics, energy is a Hermitian. So the eigenvalue is a real and measure time momentum and energy, the real quantities. So eigenvalue is a real. You can measure all the physical quantities. What is limited? This is of this type. Whenever a state evolves, for example, in quantum world, you want to rotate, you want to shift, you have to do these limited matrices. So in quantum, you are touching this exponential advantage from the in natural quantum world, whatever you want, you have to check the matrix has to be. If it's not, somehow. Hermitian objects are measurable. They are measurable. So any operation mark. Very good. So one gate I have introduced is called a single qubit gate. Done. So now you see the difference in the quantum world, classical world. Classical world, nothing happened, state quantum world, state changed. But state is not lost. Okay. And that change through measurement depends on the basis. 0, 1, plus minus, or surprise polarized, create surprise polarized measurement also. Okay, so whatever basis you use, one measurement will lead to collapse. Many measurements will lead to statistics. So this is called measurement statistics. That will be called measurement statistics. That is very useful. If you don't believe that how useful it is, so let me give you some examples. So first of all, whatever this measurement we have done, have we got technology out? Now you see comment whatever programming does tells us what is the technology, what is the product. We Indians are always thinkers, we don't come up with any technology. Now you see Americans are there, so what they have come up with technology. What is the technology? Random number generator. Quantum random number generator. That comes is completely arbitrary nature of and see what quantum Rn. Because this collapse of the wave function is completely statistically arbitrary. So through the product, you can really generate random numbers. You can see in this least DLAB, joint DLAB, least in the center, they are continuously broadcasting quantum numbers which you can use and do your Monte Carlo simulation. In case of Monte Carlo simulation, you need it. So MATLAB, for example, MATLAB, there's something called random numbers. What is that thing called? Dan, start Dan or something. This starts Dan, random numbers, but they are not really random. They are random numbers. calculation using multiple is not useful. But if you use list or Gila Sentinel, right now also can check it. Random, your answer is better. Faster. So now in product market is available. You can check out the one you can buy. What is also useful? Again, engineers, Bennett and Prasanta. These great names. Very profound was IBM on computer head. So they were in Bangalore. So they heard some people talking about this kind of thing, collapse or the wave function. And this British person was trying to impress them, the engineers, Prasanta from Montreal. And he demonstrated some of these things when I was there. It was the 93. Bennett and Prasanta, they thought about this. Physics people always trying to confuse us. So what is the bottom line? Bottom line is wave function collapse and arbitrary. They say let's use it and we use it for quantum physics. Quantum. Actual fact, I'm not getting story. Somebody has already done it here. I think RTC has done it here. Quantum physics. Check. Very nice topic here. Very quickly explained. Basis of measurement is only measure. You can see now in the market, one of the leading content container for the generation is QIQT. So nothing except measurement. Now only you can see the technology. Only last month or even last month on the media, where the rules clear about it, like document is in the public domain, you can check. And you can see we have not moved very much forward. And this is beautiful. Please look at the start. This is very beautifully resource and this horizontal, vertical, that kind of arrow, this kind of arrow, all so that you are familiar. Only memory. And so basically create single photons. So what the technology you need single photons you have to create, then you have to detect. So detector and creation of single photon is very important. That's what you buy from abroad. For example, these people going to experiment, they will do little more, better. They take a nonlinear system, they create entanglement. Photons are joined, they have created one of the materials. But after it was created, only measurement. So this is actually was a little more developed thing. You can check what's RPC, what's processing, RRI, they have done it. Only recently. Very, very recently. For example, there was a big news in the newspaper 15 days back. So processing from RRI has shown that once source is moving, other two is static. They can do this little improved version of QIQT. You check out that on the website. Yes. So those things are technology. Now there are companies, for example, Bangalore, there are companies you can check out outside also. People are that a package, sending quantum random generator, then this QIQT. And actually these are being used. So this is really technical. And you see technology is only measurement. Only measurement. And we believe people are trying to impress others. I'm not putting myself down. That quantum needs to collapse, linear always collapse. They say, why not? What do I do with it? It is so arbitrary. You see engineers, they're quite smart. They used it and they gave the product. And they're making money. We are still poor. Okay, very nice. Good. So classical and quantum is now clear. You can go ahead and play around with IBM. So how am I doing time-wise? How much time? So so I will tell you some more things. But then very quickly I'll tell you. I have to go to entangle photons. So what is this entanglement? People who are doing matrices, it's very simple. That for example, you take helium atom. You find that nucleus is called alpha particle and 2 electrons. Hydrogen molecule, same thing. These 2 electrons and has spin. So physics people will say spin up and down. This rotation, which is 0, which is 1. So sometimes rotational you may face a problem, but this kind of rotation. So they found that these are in a state called singlet. What is singlet? 0, 1 minus 1, 0. Now what is this yellow and right? What is this 0, 1? This 0, 1 is inner product or outer product, I don't know, but what we do is 1, 0. Direct product is 0, 1. What is it? 1 times 0, 1. 0 times. So that's the calculation. So I get 0, 1 is that here. Right? 1 times 0, 1 is and so this is next thing. About 1, 0. 1, 0 is equal to 0, 1 plus 1, 0. This is 0 times 1, 0. 1 times that equal to 0, 0. Add them up with the minus sign. That here, okay. That is 1 by 0, 1. So this is the state of the electron. Here it's actually spin combination called singlet state. What you might have seen they appear thin. No spin. Up and down the cancel, total spin will be zero. Measure the spin of the system, we have spin is like angular momentum. Spin angular momentum will be singlet. So that's what long time back we have seen. So this state is there. Now then comes Einstein and all these people. You see this imagine this helium, one flow is here, one flow is here. Instead, let me think to entanglement fluid. One is in Delhi, one is in Washington. Long. They are very fertile imagination. Those days, these kind of things are not there, but now they exist. China has a wire connecting Beijing and some other city, 800 miles or something. So Einstein in 1935, so-called nuclear paradox. These kind of paradox. So then he pointed out, okay, let me give some names to them. What is Alice Bob? Alice Bob. Now suppose Alice is here, Bob is here, far, far away. So far away, light velocity, light cannot reach for some time. You do a measurement. Alice does this measurement in what basis? As you agreed last year, choose the basis. 0, 1 basis is choose. So if Alice finds that what state is 0, this state becomes 0. 1. If Alice finds that what state is 1, this state becomes 1. 0. You see, depending on Alice's measurement, Bob's state has collapsed. But it's so far away, even light cannot communicate. That was Einstein's objection that quantum mechanics has non-local. Non-local. Not local. And theory has some problem. Since Einstein said after that, okay, board type argue, this debate is going on and on. Even now, also in talks with people for foundational physics, they will still argue with you for hours together. But reality is this, that far away, that day, you are doing a local measurement, a single measurement, state collapses instantaneously. But then people found out that information about the state collapse can only go at the velocity of light. That you will realize later, that we cannot send information faster than light. So because no signal in here, information, although the state is collapsing instantaneously, find out that the state has collapsed. That information will take speed of light. No signal. But this is what happens. State collapses. Two dots become one dot. State collapse. So this is so-called nuclear paradox. Then you will see paradox was going on and on. Of course, this year flow rates came because it showed entangled photons If this something for real measurement, you might have seen them, but I will check out later. The kind of states we need to know by conditions. And now the technology is this. Because of which reason? Again, Bennett, Prasanta, and others. Again, they said the physics people are trying to confuse us. Can you use it for something? They did something which is out of town or movies or televisions. So that is another business now. QIQT, again, quantum, random number, generator, and television. These are the things people are doing. Every day you find some newspaper. China is teleporting to Vienna from Beijing, Lhasa from Beijing, Lhasa Singapore University is doing this. These are the things which so one other day, if you are to ask me, I can work it out for the teleportation, but we find out information cannot be sent after the night. Very explicitly, you see, you will need this state already programming. This is called entanglement, maximally entanglement state. Already you cannot do it. And who did it? Again, 1993, the same year. Russia, other people. This is experiment verified. So now the conclusion is quantum mechanics is complete, but now information cannot go after that. But this PPR, this debate into Einstein has led to a lot of development. In those days, people like Niels Bohr used to get bogged. They used to refer to Einstein as old man has gone nuts. But thanks to Einstein, these questions are raised. A lot of developments took place. Thanks to Bell, it was seriously before that Bohm also in teach. We'll talk about that. So now we are in a column vector, 4 entries. Earlier we are in this domain, 1, 0, and 1. Now 2 party. The single party is 2 party. And we have heard one word called entanglement. So first you ask, how many vectors I need in this dimension? Answer is 4. What are they? One of them is here. One of the other is 1 minus 1. And if they are around a little bit, we find out the other 0, 0, 1. 1, 2. 4 of them orthogonal and complex. So, if you look at it very carefully, these are the so-called Bell states. Bell showed his miracles using this. This year, right, is because of maximally intact. Big words. So when I saw it, I was very confused, like everybody. Then I played around. I found out this object is not entangled. Only one is not entangled. All ones are not entangled. And for example, 2 ones, some place not entangled. So I asked anybody who I was to meet, I would ask, so what is so special about 2 ones in this location? That these fellows are maximally entangled. Put more ones unentangled. Okay, only one unentangled. 2 ones in different location unentangled. And how about this fellow? 3 of them. So I used to ask this fellow is entangled. So there was this boy Amit who actually explained to me that why is it entangled and why is it maximally entangled. That led to a lot of my research, which is going on right now, and a very nice interpretation of entanglement in terms of example. So what was this point? This point was that instead of this, construct a matrix. This first column, first half, second half is moved here. Try for everything. Then take the determinant of this object and take this matrix. We find out that for all these Bell states, determinant of this thing is magnitude or Bell states. All the terms are non-entangled and partially entangled. In fact, it has less entangled, it has maximum entangled. So then he also explained to me that why does it make sense? His point was that let's take general states. If they are product states, then it will be alpha gamma theta gamma delta. So this information of the multiplication here constructed to white matrix. What we find? Alpha gamma theta gamma and 1 0 So that is the reason why you are then line becomes easy. So I can compute determinant, take magnitude. Good, I found entanglement. But when you have no what to start thinking, determinant is supposedly is related to area. Then can I think it in terms of area? So there was a poor boy called Billy Basper, who is now in Toronto. So my past paper came because of the hard work. And what is this area? So after that I start. So what is this area? All right. So let me take the same state at two particular state, Alice box state. So let me have most general Alice box state. So it will be alpha 1, alpha 2, alpha 3, alpha 4, 4 of them, 1, 2, 3, 4. This basis is called computational basis. That's what we use. They are the basis which is 1, 1, based on the other column is called bare basis. One which I showed here called bare basis. So these two are very famous. Bare states are bare basis. Non-entanglement, and maximum entanglement. So this fellow we can check 1, 0. Very good. So now let me do it. Let me give the name Alice form. So let me see if Alice at state 0. Because I am checking if it is separable or not. If it is separable, it should be something like phi Alice and psi Bob or phi 1, phi 2. Separable. If I can write that product, then on it. If I cannot, then I have to find out is it maximum entanglement or not. So 3 questions: separable, entanglement, maximum. So for that, I depends on my basis. First I chose computational basis 0 or 1. Then I checked if Alice are 0. What is Bob? I want to see separable. No. I have to first find out Alice are 0. Bob would be alpha 1, 0 plus alpha 2, 1. Alice is 1. Here I did. Then would be alpha 3, 0. Right? Is that right? 1, 0. Alpha 3, 0. 1 plus alpha 4, 1. Looks like similar, except the coefficient. Now, when it is separable, right? Convince yourself. Suppose these fellows are equal. Of course, you can take that thing common, right? Alpha 1, 0 if these fellows are equal. Alpha 2, 1 equal. Then it will be 0 plus 1. If they are not equal, then the factor will come here. So that means if they are parallel, these two vectors, if they are parallel, coefficients of 0, coefficient of 1, if they are parallel, then it is not. What is parallel? Alpha 1 by alpha 3 is equal to, if these two vectors are parallel, then alpha 1 by alpha 3 is equal to alpha 2 by alpha 2. Is alpha 1, alpha 4 minus alpha 3, alpha 2, alpha 3. Check. The general state is of this type. Alpha 1, alpha 3, if I remember correctly. Then alpha 3, alpha 4. And the matrix is alpha 1, alpha 2, alpha 3, alpha 4. And indeed, determinant is this. So therefore, the conditions are just parallel. It is also in parallel. So that part is clear. Now going into the maximal entanglement. So that there are our working here in COVID time, and Mithilesh, Darby, other, Vinas, many people are here. They found out if these two vectors, now look at these two vectors. Here vectors only in the xy plane, yes or no? X is like 0, like 1, here are vectors. Parallel means this. In fact, their magnitudes are same, normalize it. If they are perpendicular, if the area is the maximum between these two vectors, 90 degree, they entanglement maximum. So this is called concurrence. So in fact, you can actually show concurrence in the area. Then of course, beneath a very anxious toy, immediately pose and the kinds of the area, any big state also takes multi-qubit. For example, then you can just into this so-called GLZ state, CW. Then for Gallagher got issues for price. This state, another state it takes this kind. 0, and ice. A very well known state, GLZ and W state. And bipartisan means entanglement into two parties. So one is called Alice, other is called Bob. And any kind of bipartisan you get, and in fact all sorts of bipartisan you have to check. And it finds then, so this paper is there, so someone can check my scholar account, the site is 47. So you can actually interpret whole thing like an area. He needed some theorem like Schwarz inequality, found out that is due to Lagrange, cited as Lagrange inequality. But after the paper got accepted, somewhat like Schwarz inequality, the one person from MIT pointed out that this was known to Brahmagupta. So Lagrange and Brahmagupta. In fact, then I leave it to you that how Brahmagupta discovered this identity. It is like triangle inequality, A square plus B square equals C square. Those kind of things are there. Then there was another Patel boy, Aryaman Patel, always mouth shut, knows how to calculate. So he actually took this kind of things to mixed state. That people is also there. Mixed state, we both computed geometry, some phone I also don't remember. That people is also there, which use as access. Aryaman Patel, Sriya Banerjee, and myself. So completely Sriya and myself are another paper. And later on, for example, now this project we have done it now instead of QIQT. QIQT. What is QIQT? Three-dimensional space. Dealing like XYZ or dealing with still one. This work is currently almost published. Sumit is there. Sadly, to this piece of work with Sumit has gone to Canada. All work with various others. Sumit is soon going to flee to Australia. So they arrange something for him and his work is this. And here it is urea. Here it found this is volume. Area completely geometrical. So therefore, because the vectors, the nature of entanglement, the vectors in parallel or perpendicular can be almost completely geometrical. Now, is it actually over? So you know, and if some of you are good, just check Joe Everly plus another person 2023 PCM. There is a archive paper. They actually show that their measure of entanglement is the best. So beyond two particles, maybe three particles onwards, not much. They use triangle inequality. Okay. You can request your people who are here, they will send you. Some of you are smart, let us see. They come up with a geometric understanding of what Joe Everly is telling. For example, you we have done for two particles. So the whole thing is actually open. Where do we this kind of thing physically manifest? For example, if you like proton, protons wave function is made out of three parts. Three parts are exactly like this. So proton wave function is text. It will be upward for the UD, and some many terms. So the wave function has all sorts of degrees of background, screen, color, flavor, everything is there. But out of upward from downward, that wave function is highly entanglement. To understand the property of the wave function, the entanglement will play out, just like in case of singlet, we found anti-ferromagnetic side of singlet. So, for example, Professor Chiranjeev Rao came here, he actually used this singlet theory to describe anti-ferromagnetic. First experimental manifestation of concurrence in a spin chain. So check it out. Chiranjeev Mitra, beautiful Nature Physics article. Nature Physics article. And plus collaborators. That spin chain is made out of copper, water, something like that. Sample came from here, Padin Monroe's group. So concurrence, how we connected susceptibility. So I remember this kind of plot, and it was found that when concurrence becomes zero, susceptibility has met. At this point, some measure of concurrence that you have to check in the presence of magnetic field and spin. So this point, I think this may be the function of P or something like that. At this point, concurrence becomes zero. Still, I don't quite understand that this concurrence, why in fact susceptibility becomes highest in this. Then I was also there, so there is another kind of pattern of correlation for discord. We found experiments, and we have one here. Even if concurrence is zero, discord is still there. Some kind of pattern correlation. What to do with discord? For example, concurrence, I know how to use it for teleportation. What to do using discord is still a question. Some people have shown, and you can do some quantum task using discord. For example, here it is present. So what is it doing to this anti-ferromagnetic IM1? So a lot of open items. For example, Chiranjeev's work was so nice that Nature Physics asked him to write use another physics first of all. Then really a nice article. Nature Physics asked him to write something like 2013 February. So he wrote because of his work. That was the first experimental work where concurrence manifested in susceptibility. It really is very good. So very good. Now, if and you truly are smart people, I must believe that you can do better than me. So let us see how quickly you can work out Everly's paper and come up with a paper. So I'll see you then. Thank you very much. Any questions? How many of you are here? Wasting your Saturday. So any questions you can ask? If not, then today also there is one more tutorial, right? So I can actually take a look at those papers. Our people will send you those papers. We have already collected them. Okay, on your own also can check. Actually, honestly, there are lots of open questions beyond 2 part, completely unknown one. And what they physically imply, even now also, you see Joe Overly was my teacher, 89-year-old man now. Now he has shown that same good old triangle inequality and something else, geometric interpretation, and his measure of entanglement is the best. And if you check my work using this same idea, last year we actually did explain this double slit, triple slit experiments. The 2022 PRA paper, we sent a copy to that to you. And entanglement for continuous variable, how to use it. Vineet Bhaskar right now is having a job in a company which has both quantum computation and IIML in Toronto. So very nice thing to play around at home you can play and find out new methods. And I add that I completely assure you, beyond 2 particles, even 2 particle mixed state is open. You can significantly contribute if you want. Okay, so very good. See you then.